My favorite thing about engineering has always been how I can apply what I've learned in the classroom to real life. So today, I'm going to show you some thermodynamic concepts in cooking. In this tutorial, I'll be making a simple garlic bread using just white bread from any store, a little bit of butter, and some garlic salt. Let's talk about the second law of thermodynamics. There's no simple statement that captures all aspects of the second law. There are several formulations of the second law. For our specific application, I think the Clausius statement encapsulates the second law the best. The Clausius statement basically states, in a simple system, heat energy will always flow from hot to cold without any external intervention. We can treat our stove as a hot thermal reservoir. This is because although it does lose a small amount of heat, compared to the entire system, it can be considered negligible, and so the reservoir stays relatively the same temperature. In this example, the pan is the cold reservoir, and so we have a heat transfer from the hot reservoir to the cold reservoir. In thermodynamic analyses, it's very important to define a system. A system allows us to simplify the problem as needed, as well as help us to solve what we're looking for. In this case, as mentioned before, the system we're looking at is the hot reservoir, which is the stove, and the cold reservoir, which in our situation is the pan, and the heat transfer between the two. As I finish up the diagram for a thermodynamic system, I want to begin talking about irreversibilities, which will be the last topic we cover. Irreversibilities are properties of a process that cannot be reversed to restore the system or its surrounding to its exact original state, without any external change. Although in this application, it's pretty intuitive why this cooking process is irreversible, that's not always the case. Think of water, for example. Water melting can be seen as a reversible process in a general sense, but in a purely thermodynamic view, it is not reversible because the entropy of the water increases. Simply put, entropy is a measure of disorder of energy in a system. And think about water. When it melts, the disorder of the water molecules increase, and therefore the entropy also increases. Right here we have a side-by-side comparison of two pieces of bread, one that we just toasted and one that just came out of the bag. As we can see, obviously they're both different. Cooking involves various chemical reactions, which end up causing irreversibilities. Although all actual processes are irreversible, for simplification of engineering analysis, there is conditions in which we'll consider ideal processes without irreversibilities. No AI was used in the filming of this video. All sources came from the Fundamentals of Engineering Thermodynamics textbook as well as class notes.